All right, welcome back. So now we're going to do Unit 6, Lesson 2. And that has to do with instantaneous rate of change. So once again, just to review, a secant is when you have 2 points on a graph and you connect those 2 points with a straight line and you find the slope. Usually that's what you're looking for. The average rate of change has to do with the secant. So the secant line is called this line, and the average rate of change is when you find the slope of a secant line. The instantaneous rate of change corresponds to the slope of a tangent line at one specific point on a curve. So tangent line, you pick one point on a graph, and then you draw a line that only intersects the graph at one point. And when you find the slope of this tangent line, that is called the instantaneous rate of change. So I'm going to show you how to do this. Okay, let's say we have example 1. The height h in meters after 2 seconds is modeled by this equation. Determine the average rate of change of the height of the ball for each time interval. So the first interval is between 0, 0.5. So this is my x value or t value. So these are my t values in this case, my independent variables. So t1 and t2. So we're going to have to find h of 0, which, plug in 0, you have negative 4.9 times 0 plus 14 times 0 plus 1. That's just going to be 1. And then you have h of 0.5, which is equal to negative 4.9, 0.5 squared plus 14 times 0.5 plus 1. And let's see, 0.5 squared, 0.25, then times that by negative 4.9. And plus 14 times a half, which is 7 plus 1. So, yeah. Once you do all that, you should get 6.775. And now we have our y values and our x values, or, our independent and dependent variables. So we can solve for slope. Slope is, remember, t2 minus t1 over h2, which was 6.775 in this case, minus, and then h of 0 was 1. So that's going to be 5.775 divided by 0.5, or times it by 2, which is 11.55 meters per second. So that is the first slope between these two intervals. It's very similar to secant, and I'm not going to do the other one. I'm just going to show it to you because it's pretty straightforward. You do the exact same thing, except with the intervals between 1 and 2.5, you plug in 1, you solve for your height, you plug in 2.5, you solve for your height, and you subtract your heights divided by, the difference in your times, and then you get a nice rate there. So basic stuff, nothing new. But now we're going to do something different. We're going to do this. So part 2, find instantaneous rate of change from a graph or table. So the exact rate of change of a function at one specific value of the independent variable can be estimated using average rates of change for small intervals of the independent variable. Essentially what's happening is we are going to choose 2 time values or 2 independent variables, but a very small interval, meaning time values are very close. So the example could be something like, let's say let's say we want something close to 1 second. So 1 second, and what's a number that's very close to 1 second? You could say 2, but that's pretty far. That's like double. We want something closer. And some of you might say 1.1. And you'd be right. 1.1 is very close to 1. But guess what? We have a number even closer than that, 1.01. And we can keep getting closer. 1.001, 1.001, and so on. So this is the kind of theory that we're going to use. We're going to use a very small time interval, and that's going to give us essentially the average rate of change, but it's going to be such a small time interval that it's going to become the instantaneous rate of change because those 2 values are so close to one another. It's as if it's 1 point as opposed to two separate points. So in this case, find the instantaneous rate of change of the height of the ball at 2 seconds. So this is the equation, and we want to find the instantaneous rate of change at 2 seconds. So one of our values should definitely be, well, it depends. What are we trying to do? Let's see. Okay, so the first method that we're going to learn is a little bit, I don't know how accurate this is, but we can definitely, this is a method. That's drawing a tangent line. So you find t equals 2 seconds right over here, and then you draw a line that's touching that graph at exactly that point, and then you're just extending it. And when you do that, you can pick 2 points, and clearly I'm off by a bit. So there you go, something like that. And then now you pick 2 points on this line, this black line that I drew, and you find the slope using any 2 points on that line. In this case, they'd use 3 and 4 and 3.5 and 1. So 3.5 minus 3 and 1 minus 4. You get negative 6 meters per second. That's one way, but I'll be honest with you, that's not a great way of doing it. But it is one way. Another method. Method 2, surrounding interval, meaning look for intervals that are next to 2. So we have 1.5 and 2.5. They're both exactly 0.5 away from 2. We find our y values at these points. Just plug it in. So h of 2.5, h of 1.5. Plug into the equation. You get negative 11. Sorry, you get 5.375 and 11. And 2.5 minus 1.5 is 1. And you get a rate of this. This is definitely good. So this is one way of doing it. Finding, so the point that you're interested in, you look for, so our point, the question asks for time at 2 seconds. We wanted to know the instantaneous rate at 2 seconds. So we chose 2 points, one right next to it on the right side and one right next to it on the left-hand side. And then we took the average, essentially, or slope formula. So that is one way of doing it, for sure. We have another way of doing it. Interesting. Method 3. I usually prefer one of them over all the others, but that's fine. We'll go through all of these. So method 3, we have averaging a preceding and following interval. What does that mean? So we find the average rate, or like the secant. We draw a secant from the first point that's right next to 2 and then including 2. So this is a line that's here, so I'm going to find the slope from this line to this line. We get negative 3.2. Plug it into the equation. Then we're going to pick 2 as a starting point and pick the next value here and find a secant, draw a secant, sorry, and find the slope of that secant, which is going to be, in this case, negative 8.05. And then we take the average of these two values, and that will give us our instantaneous rate of change. So a few different ways that we've done it. One, remember, was drawing a tangent line and figuring the slope out using that tangent line. I don't really recommend that. I like this one overall, to be honest. I like the one where you have the point in the middle and you just take 2 points next to it. We're going to get into more details. There's better ways of doing this. And then this is the averaging the preceding and following interval, which this isn't bad either, because it depends on what the graph looks like and whatnot. So yeah, let's do an example now with a table. So here we have a table. Example 3. Consider data from Bank of Canada for beginning in November 2007. Estimate the instantaneous rate of change of the value of the Canadian dollar on November 7th. So November 7th is our point in which we want the instantaneous rate of change. So how can we do that? So we can't really draw a graph because there's no graph, so we can't draw the tangent line. I wouldn't recommend that ever. One way is to find a value before and after it, and then draw a secant from this line to this line, and find the slope between those two lines, right? So for example, we have slope is equal to, and the interval we want is between 5 and 8. Something I should mention, if you don't know, when you're given a table, usually the independent variable is always on top, and the dependent variable is the bottom here, in case you're confused. And if it's a table like this, usually the left-hand side is always x and the right-hand side is always y, just so you are aware. All right, so we know slope is y2 minus y1 over x2 minus x1, so x1, x2, you could say. So this is going to be 8 minus 5 on the bottom here. And the value for 8 is 93.06, and the value for 5 is 93.39. And if you subtract that and divide it by 3, you'll get negative 0.11 cents per day. So the units are always given here. So J cents. So that is the slope, or that is the instantaneous rate of change. Meaning on day 7, the value of the Canadian dollar is decreasing by 0.11 cents per day. That was method 1. We're going to now do method 2. Method 2 is a little bit more different. And it's actually more accurate. So we're going to take the average of the interval before it and after the point that we want. Remember, our key point was 7. So in one scenario, the interval is going to end in 7. The other scenario, the interval is going to start with 7. So pretty simple stuff. We are going to, here, let me get that chart back. We're going to need this. All right, here, let me move that there and there. Okay. So 5 and 7, we know slope is going to equal x, remember x1, x2, so 7 minus 5, and then 5, the value is 93.39 minus, and the value of 7 was 91.70. And that's going to equal a number which is negative 0.845 cents per day. Always important units. For the interval 7 and 8, same thing. We're going to do 7. Remember, x1, x2, 8 minus 7, and it's 93.06 minus 91.7. And if you do that correctly, you get close to 1.36 cents per day. And now we're going to take the average between these two values. So we're going to add them together, and we're going to divide by 2. So let's see. Let's do that right now. Okay, so yeah, I did the calculations. So when you add them together and divide by 2, you get, here, I'll write it out for you. So negative 0.845 plus 1.36. And you get 0.258 round. 8 is rounded cents per day. So that is more closer to the actual instantaneous rate of change. And yes, that's this question.